So why do we experiment in industry? I think we experiment to maximize value and minimize harm from our decisions, and that we care more about the magnitude of our errors than their frequency. And so I'll offer this introductory example of, when choosing a ride home for your son, Junior falls off his bike less than 5% of the time on Route A, and Junior also falls off his bike less than 5% of the time on Route B. And so we're going to revisit this a few times when we think about frequency versus magnitude. So over the past 2 years, Intuit shifted its A/B testing criteria away from statistical significance toward Bayesian risk in order to reflect our priorities that minimizing potential harm and maximizing benefit should steer timely decision-making. This has reduced our test duration by over 60% relative to significance testing, and this has allowed us to roll the best possible experiences to the maximum number of customers as fast as possible. And the remainder of my slides will cover why and how we did this. So part 1, significance testing limits the frequency of errors. So even for A/B tests with a true difference of 0, you can still observe a range of differences on your tests. And that's my x-axis here. What is possible to observe in your test samples when you have a true difference of 0? And so given the sample size and standard error, you can easily, in this case, observe up to a 2% difference in either direction when there's a true difference of 0. But significance testing, it introduces a threshold so that only the most extreme outer 5% of observable differences is considered significant. Okay, and that limits our false positive error rate to 5%. If you follow all the rules about peaking and multiple comparisons, et cetera, you can still maintain a frequency of error rates. And so, this more extreme, 3% difference, this would be considered stat sig. It's beyond the threshold. This 1% difference would be considered not statistically significant. Now, even if it is a real effect, it's not statistically significant. In that case, it's a false negative. It's a failure to detect a real effect. And so that's how we limit the frequency of our errors. So we can cap our false positive rate at 5%. We often target a false negative rate of 20%. And this seems to present false negatives, which are failures to detect a real effect, as being 4 times worse than false positives. And I think this is justifiable for scientific research, which prioritizes knowledge building and places such a high priority on the integrity of its claims that it would rather fail to detect a real effect than report an effect where none exists. But are these priorities justifiable in industry? Because what is the cost of a false positive effect in industry? In most industry A/B tests, the cost of a false positive is 0, but the cost of a false negative is never 0. And this is because in industry, nearly all costs are sunk by the time the test begins. All of the designer hours, all of the developer hours, these are all sunk by the time you have the experience launched in your product. The final decision to roll it out is turning a knob up to 100%. Now, there is a subset of tests that have high relative post-release costs, such as an expert platform where every additional engagement incurs a cost, or an expensive LLM, in which case just adjust your metrics so that 0 reflects your break-even point. You're essentially reporting on profits instead of revenue now. But again, that's not most tests. Most industry A/B tests are UI changes. They're simpler tests. And so if you truly have a false positive and you roll this treatment, then you're by definition offering customers an equivalent experience to the one you've replaced. But if you fail to detect harm or you fail to detect benefit, then you're quite literally harming or depriving your customers. All right, so part 2, Bayesian risk-based testing. Okay, so back to Junior. Okay, would you rely only on error frequency when choosing a route home for Junior? Okay. What is the difference between these two scenarios? It's the magnitude of harm. And I want to offer you this calculation of risk as the probability of harm times the average magnitude. So in the grassy field scenario, Junior falls off his bike 5% of the time, but There's practically no risk of a fatal accident. Maybe like 1 in a billion times something disastrous happens, but you've got 5% times essentially 0, so there's almost 0 risk in biking in the grassy field. That's why we teach our kids to bike there. But on the cliff's edge, usually he doesn't fall, but when he does, he's losing 60 years of life on average. So every trip on the cliff's edge is a 3-year expected loss of life. And so when choosing between these two routes, it becomes a no-brainer to, go on the grassy field. And so we could connect this something more familiar to an A/B test in industry, where maybe you're doing an A/B test of the existing user interface versus a streamlined user interface that has like 20% fewer steps. And you see that, I've got a 1.5% higher conversion rate in the treatment group B. So what does your business care about estimating from this data? All right, so you've seen a 1.5% difference, but there's a range of real differences that could have generated your sample, okay? Do you care about estimating what is the most probable reality given the data I've collected? Or do you want to know the probability of your data under an assumed reality? And I think this is a pretty obvious choice. You want to know what's real, what is probably real in light of your data, but that's not what you get from a significance test. A significance test is telling you the probability of your data if reality is 0. So these are not the same thing. The probability of your data, given a reality, is the likelihood function. And that's what I've got expressed here. There's a range of potential real effects on the x-axis that could generate your 1.5% data, some more likely than others. And when you look at this distribution, you might notice, I've got equal likelihood that a 1% real effect and a 2% real effect could generate my data. They are equally likely to generate that data. But I want you to ask yourself, do real effects of 1% and 2%, are they equal? Sorry, I've already said that they're equally likely. Do you encounter 2% lifts with the same frequency that you encounter 1% lifts? I don't know about your companies, but I see small effects with much greater frequency than I see large effects. And you want to bring that information into your model, okay? Because when you bring that into your model, this is going to allow you to now compute what is the most probable reality, okay? And so in this case, I'm introducing this new term, the prior probability of reality, and that's the dotted line plot that you're seeing. And this is saying that, hey, look, most A/B tests have no effect. So that prior probability of reality, that is centered at 0. And I'm saying, hey, I'm open-minded. I could have up to a 1% effect, on this given test. And when I combine these signals, I get my posterior distribution. This is the probability of reality given my data, and that's represented in blue. And it's combining the signals from the likelihood of our data with our prior probability. And this is the thing we all want. And it's saying, hey, I now have this expression of a range of effects that could be real, and now I can calculate the risk of making a decision under uncertainty. So this is a more conservative estimate. I'm not estimating that I have a 1.5% lift, even though that's what I saw in my data. I have a more conservative estimate, but I can ask smart questions now. I can say, hey, looking at this range of what could be true, how much of it is harmful? What's the probability that I have a harmful effect on my hands? In this case, it's about 10%. And I can say, well, how bad does it hurt? On average, it's a 0.2% loss. This would be, a 0.2% loss to conversion when a harmful effect is true. And remember the risk calculation, probability of harm times average harm. So now I have a risk estimate of 0.02%. That's my expected loss if I roll out this treatment. And there's uncertainty and risk in every decision that we make, even if you're choosing to revert to control. A lot of times in a significance test, reverting to control is the default. It's considered the safe course of action. In business, it's often not the safe course of action. In this case, I have a 90% probability of harm if I revert to control, and the expected loss for reverting to control is a 0.5% loss on conversion. Whereas, if I roll out the treatment, I'm only expecting a loss of 0.02% in the unlikely event that I'm wrong. And this is actually a harmful real effect. And so you could run A/B tests this way. You can compute the risk every day for every variant and stop your test when the risk of making a decision is acceptably low. So in this case, I've got the day of my test on the x-axis, and I've got the risk from choosing either variant on the y. And so around, day 6, recipe or variant B has breached my risk threshold. This is a safe time to make a decision. But this brings up, what is a risk threshold and how do you set it? I came across the idea in this great paper by Chris Stuccio. You can find this readily online. He actually offers all the Python code too for how to calculate expected loss, which is the term he uses for risk. But I found it was very subjective and ambiguous about how to calculate the threshold. So the quotes from the paper would be like a threshold of loss which is considered acceptable, or when your expected loss drops below a threshold of caring. He offers a concrete example of a 2.5-cent loss being considered acceptable. But you can't leave this up to stakeholders. They're just going to be paralyzed. What is a penny, is a nickel? How much is an acceptable amount of risk to take? But the good news is you can validate a safe risk threshold using data simulations using your business conditions. And that way you can supply that to your stakeholders and they can feel confident using this method. And we're going to do this through data simulation. And so the way that you do this, if you haven't simulated data before, is you want to start off by simulating what I call a daily reality. So I've got test ID number 1 here, first day of the test. And I have 2 variants, and I'm assigning a true rate for each one. So variant A has a 50% conversion rate, variant B has a 50.5% conversion rate. And now I have 1,000 trials, it would be 1,000 customers for each. And now you're going to simulate the number of success events. Okay, so using Python code, you'd just be using the NumPy random binomial, and you're feeding in the number of trials and the true rate. Okay, if you're going to use R code, you're going to use R binom, and same variables. But this is going to simulate a random number of events based on the parameters you've supplied, and this is going to kind of bake in that sampling error. And now you have, for day 1, you have a number of success events and you have an observed success rate. And you're going to do this for 100 days per test and 1,000 tests total. This is a daily reality, okay? And again, you don't need to even know how to do this off the top of your head anymore. I mean, they're just prompting your preferred LLM. Please generate Python or R code to create a data frame based on these parameters is going to get you what you need. Okay, so you're going to take that daily reality, and now you're going to turn it into a cumulative reality. Okay, so now you'll notice that my trials aren't 1,000 per day anymore. I am doing a cumulative sum. So I have 1,000 trials on day 1, and then that accumulates to 2,000 trials on day 2. And you're just going to group by your test ID and the variant, and then you're going to get the cumulative sums of trials and events. And that's going to allow you to also compute the cumulative rate. And so this would be, for every A/B test you're simulating now, you would have the daily cumulative stats. And again, trivially easy to just prompt an LLM to generate this code for you. Okay. So now you're monitoring the daily risk estimates for every test, and you're going to stop these simulated tests when your threshold is breached. So this is just on test ID number 1 here. I breach around day 6. And I'm just, again, showing that, you're doing this across all of your simulations. And every time there's a breach, you're going to record what decision was made, how large was the sample, what was the day. And now you can look cumulatively at what does decision accuracy look like in 1,000 simulated A/B tests when you're using 0.01% risk threshold. Okay. So in this case, 8% of the time, I'm wrongly choosing A as the winner of the test, and 92% of the time I'm choosing decision B. I'm making my decision on B, which was the superior variant. But I'm looking at these histograms and I'm like, oh, that's interesting. Almost all of my mistakes when I choose variant A, those are happening very early in the first, few days of the test. So what if I impose a 7-day minimum sampling period? Well, now my decision inaccuracy, I think it was at 8%. Yeah, it went from 8% down to 2%. And you can think of this as like, that's the early stage. You don't have a lot of data. You're more likely to get a more extreme sample that could lead to a bad decision. And so you can, again, these are just like insights we gained through running these data simulations. Okay, a minimum sampling period can really help calm down some of the volatile decision-making in your model. And you can also see, well, how much of a cost did that incur in terms of delaying your decision? So now I'm at 12 and 17 days, whereas before I was at 5 and 13 days. So, a 6% increase in accuracy may be worth the trade-off. Okay. But doing this kind of simulated test performance at scale, a really valuable way to help know if this is worth something to invest in. So I'm going to do simulations now. I'm using a 0.01% risk threshold for my Bayesian tests. And I'm going to compare this to two significance testing methods where I'd be looking for a minimum detectable effect of 1%. Okay, so my maximum test sample would be 400,000. And there's going to be 1.2 million people who get exposed to the decision of this test. So I'm going to have 50% conversion rate in my control, and I'm going to have a true effect of a 1% relative gain in these simulations. So how's this going to look? So in terms of deciding correctly, my Bayesian test, as you just saw previously, is deciding correctly 98% of the time. Whereas a sequential significance test or a fixed significance test, they're making a correct decision 80% of the time. We're using SPRT here as the sequential significance method. But look at the mean sample. My Bayesian test is able to make 98% decision accuracy with just 88,000 samples. Whereas a sequential or a fixed test, they're requiring more than double that to arrive at a decision. And when you have greater accuracy sooner, that means you have more time in season to have that best experience out in front of your customers, which is going to produce a greater number of marginal conversions. In this case, about 1,600 additional conversions for using Bayesian, because you get earlier rollout and you have higher accuracy. Okay, so what happens if we don't have a 1% true effect? We're targeting that, that's the minimum detectable effect, but we've only got 0.1% lift on our hands. Okay, even in this very small effect scenario, your Bayesian risk test is 70% accurate in detecting that effect, whereas you're only at 10 or 13% for your significance tests. It's taking longer to reach that decision. So the Bayesian risk is now needing almost 200,000 samples. And it's interesting to see that the sequential test is now faster, but it's inaccurate. And this is one of the things that happens with SPRT, is because you're setting a null hypothesis that there's no difference, and you're comparing that to some minimum detectable effect, in this case that there's a 1% difference. Well, what happens when you encounter a smaller than desired effect? The sequential analysis rejects that effect most of the time. By design, it is underpowered to detect that. And so it's saying, yeah, the null hypothesis is a better explanation for a 0.1% lift than your alternative hypothesis that there was a 1% lift. And again, this is all in service of it's producing more conversions. It's driving the metric forward that you're targeting. And I want to offer this that there's two ways to achieve low risk in a test. So in the top plot, you've got a large observed difference with a small sample. And this results in low risk because it essentially drags the posterior distribution away from zero. There's still a lot of uncertainty about the true effect. It could be anywhere, in that distribution, but you can be very confident that there's a low probability it's harmful and, weighted by the magnitude of that harm, it's a low risk decision. In this case, you're at about 0.02%. The other way, the more common way that you get to a low risk decision is that you have a small observed difference with a larger sample size. And that's also low risk. So in this case, the lower distribution, it's like 45% probability of harm, but the amount of harm is so small. This is the grassy field, but with a 50% fall rate. You also get a low risk decision. And I think this is really important in industry because most of the effects we see are small. And a lot of the value you can add as a data scientist in this is getting your teams to move forward. These are small effects. It's not worth running this test for another 60 days to confirm that you have a trivial difference. It's better to say early, hey, there's nothing to worry about here. Make a decision that's aligned with our business strategy and move on. Okay? And this small difference, like this was something we learned from doing the simulations. Like if you want to get your risk below 0.01% in this scenario, on average, you're only going to need 65,000 samples to get there. But if you wanted to run a z-test that was powered to detect 0.01% difference, you need 60 billion samples. Now, that's just obviously impractical, but it's just kind of driving this home of like, what do you really need to learn from your test? Are you trying to get statistical significance on everything, or are you trying to learn which decisions are safe so that you can make a decision and move forward? So our summary of risk-based testing, if you care more about detecting real effects than you care about avoiding false positives, aka free mistakes, you can greatly improve the speed and decision accuracy of your A/B tests by adopting Bayesian risk as a stopping criteria. And you can validate risk thresholds using simulation studies that reflect the traffic levels and metric values that your business typically encounters. Okay, part 3, implementation, challenges and opportunities. I call this the implementation iceberg. So you have this good idea that's floating above the water that everyone can see, but most of the work is lurking underneath. As Russ and I well know, this is 75% of the work. Is you need to establish leadership buy-in. You need to build out usable tooling. You need a training and adoption plan. And so we're going to talk about that. The first obstacle is you're changing to a new decision criteria. And to be honest, this was actually a non-obstacle. Everyone from the leadership to the individual contributors, they just got it. Make decisions when it's safe to do so and share the best experiences to the maximum number of customers. But we did a full court press. We had an intuitively designed tool. We had a white paper that was written in accessible language. We gave talks in all of the data science skill building groups. This was really important. We did team-by-team trainings with every analytics team at Intuit. If you're just going to do a mass training with 300 people in attendance, that's going to be a lot of people checking their Slacks and emails. That's not the kind of setting where people are going to ask dumb, vulnerable questions and really get over their hang-ups and start to build a relationship of trust with you that they're actually going to make a business decision based on this new method. So it was a lot of time, but we did team-by-team trainings and it was well worth it. We also did a larger, more of that mass training outreach to product and marketing teams to get them familiar with the new decision criteria. But the final nail, the most important one, is getting a leadership mandate that Bayes was the new default for in-season testing. And if you've done all the previous steps, this is an easy mandate to follow. People were quite eager to use this, but each of these steps is effectively lifting the ceiling on your adoption potential. But until you get that leadership mandate, I feel like your adoption potential is capped at like 10%. But you take all these steps and you can get full adoption of your data science change. Another one, obstacle, setting risk threshold. So what's the optimal amount of risks to stop exploring and start exploiting? This is going to depend. Like, how much time do you have to explore and how much is at stake for your decision? A framework that I found really helpful was Ron Berman's test and roll approach. So, typically when you do a power analysis, it's saying, how much sample do I need to achieve a certain accuracy on my test? And Ron kind of flips that around and he says, okay, given the sample that you have, what's the best testing criteria that you could apply to that sample? This is the reality we all live in. Like you have a limited number of customers that you're going to be able to run your tests with. What's the best decision criteria you could use in that limited sample? And so, again, I would just encourage you to use your own business's traffic and metric levels to validate one or more palatable risk thresholds for your core metrics. That could be, you could start off with like 0.01% on conversion or a penny on ARPC. It's going to vary depending on your business conditions, but just choose a few intuitive ones and run the data simulations. You'll find a safe threshold. Another important one is you're going to need to offer a default course of action for the test where no breach of the risk threshold occurs. We just tell teams to choose the lowest risk option that's aligned with the business strategy. Okay, another obstacle, setting priors. Okay, so informed priors really shine on improving your estimation precision. So when you're doing a test, there's a really critical estimate I would suggest using zero-centered priors based on the surprise rule. So the surprise rule is, if a change larger than 1% would surprise you, then use that as the standard error on your prior. So I'm saying, hey, in this case, I'm using, for a small change, to say anything bigger than a 1% change would surprise me. I'm going to use a prior of normal, 0, 1%. And that looks like this. It's saying most treatments have no effect. Small effects are more likely than larger effects. But, for a small test, this is a pretty generous prior. But the good news is that even flat priors, so that's when you say like, oh, every effect size is equally likely, and these are often criticized. They're still going to outperform significance tests in terms of speed and decision accuracy. But as you saw earlier in my demonstration, like in lieu of informed priors, you can also just use the data from your minimum sampling period as your prior. So the way that Bayesian updating works is that yesterday's posterior is today's prior. So if you say, oh, I have a 7-day minimum sampling period, the data you collect during that period is literally your prior on day 8. And as I showed, it's a way to kind of calm down the decision-making model. So again, all of these things are changes within your organization. You want to roll these out gradually. We found that releasing this with flat priors combined with a minimum sampling period was a great way to get broad adoption. And then later, we've started introducing informed priors for those really critical estimates. But your decision accuracy is not going to suffer from the flat prior, just your estimation precision. So you'll make the right choice, you'll just probably overestimate initially how much benefit it's bringing. But again, always the proof's in the pudding. Just run simulations in your business conditions and see for yourself. Another opportunity, there is no minimum detectable effect for a Bayesian risk analysis. Okay? Just remember, you don't need a reminder of this, most real effects are smaller than the minimum detectable effect that you set for your test. And these smaller than planned for effects end up being rejected by design. And the samples that do not reach stat sig, the samples that do reach stat sig will by necessity overestimate the true effect. This is often referred to as the winner's curse. If you have an underpowered test, the only samples that will be statistically significant are the overestimates. And then everyone kind of clutches their pearls when, as the sample grows after release, the effect starts rolling back towards 0. But as from that earlier example I gave about detecting a 1/10 of a percentage point lift, you can still get 70% decision accuracy in Bayes. Because even a slight improvement for any variant is going to tip the scales in its favor, because these are, on average, these are going to be the lower risk decisions. Okay. So another opportunity that just keeps coming up is validating by simulation, which also gives you the opportunity to present gains in terms of your company's key metrics. If you start talking about the benefits of adopting a Bayesian testing model, that you're going to increase decision correctness by 20%, you're going to decrease sample size by 50, and you're going to increase conversions by 25, this is going to get leadership support. They don't care about type 1 and type 2 error rates, okay? They care about business metrics. And if you start using data simulations, it's very easy to translate those obscure statistical terms into business impact. Okay, final part, applying Bayesian thinking to your entire portfolio. So when you start using Bayesian methods, you're going to have to face the low prior probability of a large success in your current testing portfolio. Every time I've seen someone give a glimpse in a talk of their distribution of effect sizes, I see one of these double exponential distributions. Most of your effects are near 0, and then there's kind of a gentle flaring outwards. And I can tell you that most of those large effects in the tails are small samples. So your real effects are going to be rather, conservative and close to 0. And so you can get faster and more accurate at calling tests, but your value add is going to be limited by the size of the underlying real effects that you're rolling out. So if you want to increase the yield from your testing portfolio, you need to increase the prior probability of large effects before testing begins. Okay, this is sometimes referred to as fattening the tails, and that's the dotted blue line here. Most of your effects are still going to be near zero. Like, you're not going to get away from that. But if you can, anything you can do to fatten the tails is going to just exponentially increase the value add from your testing portfolio. And this is an example from Intuit, where in the past year, we really leaned into causal inference to help fatten the tails on our testing portfolio. And so this was a test around our tax expert platform. So in the control condition, you would be matched based on your needs with a tax expert. And in the treatment condition, there was this choose your own expert experience. And this was one of those zero effects. Okay? People actually didn't care that much about getting to choose their own tax expert. But what the team found was they started digging into the data in the off season to build a causal inference model. And they found that this availability feature did matter a lot. That if any of your matched experts were immediately available to start your tax filing, this greatly increased the probability that you would finish your tax filing with an expert. And so again, they had looked at all of these other matching categories, but this was the one that stood out initially just as a strong correlation. But they went in, they controlled for all the potential confounders, and they said, look, this is holding up. This is a very promising lever we can pull. And that became an actual A/B test that we ran in the past test season. And I want to give credit. The people in these photos are not tax experts. They're the causal inference team that did the modeling. But this turned into one of those findings that held up in the season and is like fattening the tails of our testing portfolio. And this is something we've been leaning into, just pairing our local business domain experts with modeling experts, because it forms this really powerful partnership. The local business data analysts, they have the intuition, they have the domain knowledge about what might matter, but they don't necessarily have the modeling skills about how to test that. And so we've formed a causal inference team and a predictive modeling team to support them in testing those intuitions in the off season so that we can get more of those fat-tailed ideas into our pipeline. And so a final summary is that in industry, I think we experiment to maximize value and minimize harm from our decisions, and that we care more about magnitude of errors than frequency. Bayesian risk-based stopping can slash your test duration while greatly improving your decision accuracy and business performance. The gains from faster and more accurate testing methods are limited by the size of underlying effects that enter your funnel, so you should invest in causal inference at the pre-testing stage to increase your prior probability of large and sustained effects. And so in closing, I just want to say that I stand up here on the shoulders of some giants. Some of these giants are on the smaller side, and some of them are very tall. One of them seems to hold the world on his shoulders, but if you want to move mountains in your organization, it really helps to have a team of giants behind you. So thank you very much.